Okay, so let's get started since we're 8 past now. Hello everyone, welcome to COMP2521 Data Structures and Algorithms. So let's talk a bit about what this course is going to be about. Right, so obviously this course is called Data Structures and Algorithms, so you're going to be learning about data structures and algorithms. So what are these things? We'll look at them, we'll talk about them a bit later. Right. But what this course really is about at its core is that it's about the fundamentals of computer science and of computational problem solving. Right, so this course is all about problem solving. And in COMP2511 or COMP1911, which is what I imagine most of you have done previously, you learned about the basics of programming. Right? You learned about variables, you learned about if statements, while loops. You also learned about arrays and linked lists, which are some basic data structures. Right? And you used them to solve some relatively simple problems. Right? But in the real world, many problems are more complex than the ones that you solved before, and they need other data structures and algorithms to solve efficiently. Right? So I mentioned efficiency. Right, so when you go about solving a problem in the real world, there are many choices that you can make, right, about what data structures you can choose, what algorithms you can choose, right? And the choices that you make are going to make all the difference between whether an algorithm is going to run very efficiently or whether it's not. Yeah.
Are these slides available on the site?
Not at the moment. We'll put them up at the end of the lecture. Okay. So, yeah. So many problems in the real world, they need data structures and algorithms to solve efficiently. Right. And the choices that you make really make all the difference between how efficient your solution is going to be. Right. And if you make the right choice, then your algorithm is probably going to be able to run efficiently for thousands or hundreds of thousands or even millions of inputs, right? But if you don't make the right choice, then it might not be practical to use the algorithm, right? So what I've just mentioned is true for really any field that you decide to go into in your programming degree, right? So whether you go into databases or networks or AI, it's all about the data structures and algorithms. Right, so that's what we're going to talk about. Okay, so when me or your tutors say that this is one of the most important courses you're going to take in your degree, that's probably true. It's not going to be the most career-defining degree. What we're going to talk about in this course has been established since the 1900s, right? Since the 1970s, 80s, or even before that, right? But all the stuff that we talk about is still going to be relevant today, all right? So this course is an important foundational course. All right, so what is the goal of this course? Right, so it's to take you from a programmer, which you became in COMP1511 when you learned programming in C, and to turn you into a computer scientist, right? So what should a computer scientist know? We should know about fundamental data structures and algorithms. You guys already know a couple of those. We should be able to reason about the applicability and effectiveness of data structures and algorithms. Right? Applicability in terms of, is it the right data structure or algorithm for the problem that I'm choosing? And how effective is it? How efficient is the data structure or algorithm that I chose? All right, and we should be able to analyze the behavior of our program. So, how efficient is our program, or what are some other properties that our algorithm has, and whether our algorithms are correct. Okay, so since you're in COMP2521 now, we assume that you guys know how to write a program in C, right? Given a problem, you guys know how to write a program to solve that problem, right? using simple C constructs like if statements and while loops and for loops. And also we expect you to be able to use simple C data types and data structures. Right, so arrays, linked lists, and structs, right, and pointers. So this course is going to be, we're going to be using C in this course, but I wouldn't call this a course about C, right? Because the reason we're using C is because you guys learned C in 1511, so we're just following on from that. But this course really is about the problem solving aspect, right? So we could have taught this course in other languages. There are other data structures and algorithms courses in the world that use other languages like maybe Java, maybe Python, maybe C++. And the data structures and algorithms that we cover in this course, you're going to be able to implement in any of those languages, right? So it's all about the problem solving in this course. All right, so what are you guys going to get out of the course? You're going to learn about a bunch of data structures, right? The main ones are going to be trees, graphs, and hash tables. We'll throw in a few more data structures like tries. We're going to learn how to analyze our data structures and algorithms. Right, so how good is our algorithm in terms of how much time it takes, how much memory it takes. Right? And we're going to learn about a bunch of algorithms like sorting and searching, and we're also going to learn about some graph algorithms. Okay, so at the end of the course, you should be able to do these things basically. So now that after the course that you've learned a bunch of data structures and algorithms, you should be able to implement solutions to a wider range of problems, right? Because you've got all of these new things in your toolbox, right? You should be able to analyze the performance characteristics of algorithms. So these are things like efficiency and other properties, and also the same for data structures, and also make decisions about appropriate data structures and algorithms. So given a problem, what is the most appropriate? Because there are a lot of different choices you can make. All right. So that's what this course is going to be all about. So who is involved in the course? So first of all, we have John Shefford as our convener. So he's going to be helping or really leading things behind the scenes. I'm going to be your lecturer. Our admin is going to be Ethan Brown. You would have seen his post on the forum. And we also have a bunch of wonderful tutors who will be helping you out in tutes and labs. All right, so here's the course website. It's on WebCMS. And if you want to contact us about any admin-related things, please email this email address, cs2521@csc.unsw.edu.au. Okay? Please don't email me or Ethan or John directly. Email this email address so that all of us will get the email and we'll be able to reply a bit faster. Okay. Cool, so let's talk about the different aspects of the course. Right, so obviously, first of all, we have the lectures. Right, we have one right now. We're going to have another one on Thursday, and they're both going to be in this room. And we're also going to be live streaming them, so that's nice. And the recordings will be up on YouTube, pretty much right after the lecture, because that's how YouTube live streams work. All right, and we're going to go through the theory in the lecture. I'm also going to write some code in the lecture to solve various problems. But just keep in mind that the main focus of the course is on the concepts, right? The algorithms, the concepts. It's not like not the most important thing is about the programming, right? So the programming is second. Right, so the focus is going to be on problem solving. All right, now we're going to have tutorials and labs just like in COMP2511, which you guys are used to, most of you. So yeah, you can have a read about the tutorials and labs here. Right, now one thing about the tutors and labs that are different from 1511 is that some labs have a hand marking component. Right, so in 1511, I believe most of the labs or all of the labs were auto marked, right? You just submit your code and at the end of the week or a week later, it gets auto marked, right? So some of our labs have a hand marking component because there are some activities that can't really be auto marked, right? Things like, complexity analysis, and things like your explanations, right? These things can't really be auto marked. So your tutor is going to have a look at them. Right, so the way you get your work hand marked is that when you are ready to get your work hand marked, so you're prepared to explain things to your tutor and such, well, you call your tutor over and they will hand mark your work. Right, and the important thing about this is that you need to get this done within 2 weeks of the lab. Right, so this week's lab has a hand marking component, so you need to get this done by week 3. Okay, so week 1, 2 weeks later, week 3, that's when you need to get your work hand marked by. Okay, and we have 8 lab exercises in the course, so we're going to take the best 7 out of the 8 labs. Okay. So, as well as labs, we have weekly quizzes. Yeah, question?
Sorry, you said there will be 8 labs?
Yes, 8 lab exercises. Yeah, there are 9 weeks of labs, but the last week's lab is going to be used as a demo for the exam environment. So yeah. Okay, we also have weekly quizzes, and these are going to be held on WebCMS, which is our course website. And this is going to test your knowledge of the theory. Right, so the questions are going to be stuff like multiple choice, fill in the blank, stuff like that. Right. And I should also mention that both the labs and the quizzes are due on the Monday the following week at 5 p.m. Okay. And the quizzes, we also take the best 7 out of 8. And they're worth 10% of your mark. Okay, we have 2 assignments. Right, so each assignment is going to be worth 15% of your mark. And the point of assignments is to give you experience applying algorithms to bigger problems, right? Because the labs, the problems in those are going to be relatively small to give you some practice, where the assignments are where you're going to do a lot more thinking, a lot more coding. Okay. All right, and about late penalties, so all the labs, quizzes, and assignments have the same late penalty. Right, so it's 0.2% deducted from your attained mark for each hour late. Right, so 0.2 of the maximum mark taken from your attained mark. Right, and make sure if you're submitting late, don't submit later than 5 days, because then you won't be able to submit anymore. Okay, so solutions, right? Lab solutions, quiz answers. When do these get released? So because we have extensions, right? We give extensions to students for misadventure, illness, things like that. We can't release things immediately after they're due or after the 5-day cutoff. Right, we have to wait a bit before we release solutions. So labs, for labs, the sample solutions will be released about 12 days after the due date. Right, so almost 2 weeks later. The marks, though, for labs can be released a week after the due date because that's when the cutoff happens. And the quizzes, the answers for those are going to be released 5 days after the due date. All right? So you get your feedback relatively quickly. Okay, so for assignments, now we don't release solutions for those because sometimes we like to reuse them, but the order marking is going to be released 5 days after the due date, and the hand marking, that's done by your tutors, so it's going to take a bit longer depending on how busy your tutor is. Okay, the final part of the exam, of course, is the final exam. So we have a 3-hour in-person exam, just like in COMP2521, and you need to score at least 40% on the final exam to pass the course. Okay. All right, so now, special consideration. So if you have been affected by illness or misadventure, things out of your control, you can apply for special consideration and you can get an extension, right? So I just wanted to make sure to include this because some students don't know about this, but you can apply for special consideration via MyUNSW, right? So you can check out how to apply and what evidence you need to provide over here. All right, so here's the summary of all the assessments. We have 15% labs, 10% for quizzes, 15% for both assignments, and 45% for the final exam. All right, and here is how to pass, right? Obviously score at least 50% overall and score at least 40% on the final exam. Okay, now a bit about academic integrity. So all the activities in the course, labs, quizzes, assignments are individual. So all your code or your answers should be entirely your work, right? Although all the code has to be your own work, in the labs, since the labs are more for learning, we do allow you to discuss, your solutions for the labs, but all the code has to be your own work. Right? In the assignments, we expect you to think of the solution and implement it yourself. For the quizzes, you should also work on those yourself. Okay, so I need to talk a bit about generative AI, right? Because that has really changed the world. So generative AI tools like GitHub Copilot, ChatGPT, Bard, there are others nowadays. So use of these with the intention of generating answers or solutions, we don't allow that, right? Because if you use ChatGPT to generate an answer, right, you're not doing the work yourself, right? We expect you to work on the solution, think of the solution, and implement the solution yourself so that you can gain valuable problem solving and coding skills, right? If you get ChatGPT to do the work for you, then you're not gaining these skills, right? Also, in the real world, right, ChatGPT does get used, but when you use ChatGPT, how do you know whether it's giving you the right code, whether it's doing the right thing? You've got to look at the code, right? So you need to be able to understand the code, first of all, right? And if you don't gain problem-solving skills, coding skills, then you're not going to be able to do that, right? So please don't use these tools to generate solutions for the tasks in the course. All right, but we do allow use of these tools for learning purposes. So ChatGPT can be quite good at giving succinct summaries of things, for explaining things. So that's fair game in this course. Right, but make sure to still be critical of the responses that you get, right? Because they could be wrong. It's not, large language models. It's not guaranteed that they're going to give you the right answer. All right. So what are the resources in this course? So first of all, we have the Ed Forum, right, which is a great place to ask questions whenever you need clarification of any course material, whether you need help with labs or assignments, whether you need clarification of the spec or for anything. Right, so you have that. So please join the forum if you haven't joined it already. Most of you should be added already. We also have weekly consultations. So starting from week 1, we'll have 1-hour consultations each week on Thursday from 1 to 2 p.m. So this is right after the Thursday lecture. And they're going to be in this room over here. So K17, GO2. Right, and this is for clarification of course content. So if you're confused about something from the lecture and you want me to clarify, you can come along on Thursday. Right. And even if you're falling behind, please feel free to come along and I can help you get up to speed with the content. Right. And we also have help sessions starting from this week too. So it's a great opportunity to get help with things like pointers, malloc linked lists, things like that, right, in case you're still not quite confident with those. Right, and the schedule is on the course website. Okay, so first, let's talk about the expectations. Right, so what we expect from you, what you can expect from us. So first of all, make sure to check your email regularly. Right, that's because all the announcements that we make will be sent to your email. Your tutor is going to also send you emails. Right? Some of them might have sent you a welcome email already. And we will also send out reminders of unsubmitted work automatically. Right? So maybe you forgot to submit that quiz, or maybe you completed your lab but you didn't finish or you didn't submit it. Then you'll be reminded if you check your email. Right? Another thing is, please, for labs and assignments, please make sure to read the spec before asking questions, right? To make sure that you don't ask any questions that are already answered, and that's gonna start to confuse people. Okay. And also, what we really want you to try is to try to debug things by yourself before asking for help, right? Because debugging is a very valuable skill. Right, in the workforce, you're not going to necessarily have someone behind your shoulder debugging things for you, right, whenever you encounter a problem. So please try debugging yourself. Try things like adding print statements. Try using GDB. So GDB is a debugging tool, and we have an extra lab for that on the course website. Or drawing diagrams. So drawing diagrams is especially useful for things like linked list problems. Okay. Okay. So what can you expect from us? So regular announcements and updates. So lecture slides. Ooh. Okay. So yeah, for future lectures, they'll all be released for the lecture. All right. Minimal typos and mistakes, and basically, you can expect things to be released on time. Okay. All right, so how can you do well in the course? So what advice do we have? So make sure to keep up with the lectures. Right, I know it can be hard, but try to keep up with lectures because the labs and quizzes, they require you to know the content from recent weeks. Right. Almost always, the labs and quizzes are going to be testing content from the week before.
Sorry,
Yeah.
I was about to ask if we need a particular week's lectures to do that week's labs.
Yeah. So it'll almost always be from the week before. Yeah. Exceptions might be this week because there's no week before. And please please attend your tutorials, right? The tutorials and labs are the most crucial part of the course, right? Because that's where you're going to get hands-on experience with the course material. It's also going to be where you can interact with your tutor, right? In the lecture, you might not get a chance to ask questions, right? If you're confused with something, so you leave it behind and then you eventually forget about it. But make sure to attend tutorials, right? You get a chance to ask your tutor questions and clear up any confusions. Another thing is always try to understand the course material instead of just memorizing it, right? Because first of all, if you understand something, that makes it easy to remember, right? First of all, because you understand the derivation or the process behind it. And also, the exam questions that you get are going to be different from those that you've seen, right? So if you've memorized the question and an answer, right, it might not be too helpful in the exam. Yeah?
In terms of like clarifying information, something we understand theoretically.
Yeah.
Can we go to the help sessions for that as well, or is that just for the labs?
Yes, so you can go to the help sessions to get help with clarification of anything as well. Yeah. Okay, and also programming is a skill that improves with practice, right? So the more you practice things, the more you practice coding, the easier the labs, the assignments, and the exam will be. Right? On the course website, we actually have a bunch of practice exercises. So on the sidebar, there's a link to practice exercises, and if you go and do those, then that'll be a really good practice for the labs, the assignments, and the exam. Right. On the course website, we also have a bunch of extra lab exercises. So, in this course, since we only have 8 weeks, we only have time for 8 lab exercises. But we also have a bunch of extra lab exercises that most of which were lab exercises in previous terms. And we just provide you those exercises for you to get extra practice. All right, so finally, make sure to engage with the course as much as you can, and make sure to ask questions. Go to consults if you're confused or you're falling behind, and do practice exercises. And finally, if you put in the effort, you can definitely improve. Right, so I think in this course, you really get out what you put into the course. Right, so if you put in more effort, you'll get more out of it. Right, including marks, but it's not always about the marks, right? Okay, so now feedback. So we have a feedback form that you can let us know about, about anything that's going on in the course, what you think can be improved, what you think we're doing well. So if you go to this link or you scan the code here, you'll get taken to that form, and we'll also show this at the end of every lecture. Right? And of course, there's also my experience at the end of the course. All right, so finally, some acknowledgements. So the course material wasn't all developed by me or even recent lectures. We are standing on the shoulders of giants here. So we have a bunch of old lecturers, old teachers, where this material was drawn from. Right? Even though these slides are relatively new, the material from them is drawn from the content from these wonderful people. Okay, so now we're done with the introduction. So do we have any questions? Yes?
Where can we access the
The
slides?
slides will be able to be accessed on the lectures page. Now, this current lecture is not on the course website yet, but I will post it after the lecture or during the break even. Okay? So, yeah. All right. Cool. So let's move on. So now I'm going to talk just briefly about some of the new tools and how they're different from 1511. All right, so first of all, we use a different compiler to 1511. Right, so in 1511, you would have used DCC. You probably would have even used that in COMP1911 or COMP1521. Right, in this course, we're going to use a real-world compiler called CLang. Right, there are also other compilers like GCC, but the one we are using in this course is CLang. All right, and the way we compile is by running this command over here. Right, but more detail about this in a bit. So this is the main default command that we'll use to compile things. So CLang minus WAll, this is not wall, this is WAll, minus WError, minus G, and then the stuff that you add after DCC. All right, so what do these flags kind of mean, right? The first flag, which is WAll, means to enable all warnings, right? And in fact, DCC does this behind the scenes, right? It's just hidden from you. So this will catch all the syntax errors that the compiler thinks you're making. Minus WError turns warnings into errors. So if an error occurs, the compiler is not going to compile your code, right? But if you don't use WError, if there are warnings, then the program the compiler will compile your program. But the presence of a warning usually means that there is something wrong with your program. Okay, so we use WError to turn warnings into errors and to prevent your program from being compiled if there is a problem. Right, and minus G preserves debugging information. Right, so when you use DCC, and your program encounters an error, you would have seen line numbers, right, and also variable names. So how does the compiler or how does the program know what the variable names or what the function names or what the line numbers are? That's because when we compiled, we used minus G, right, to keep track of that information. All right, and now we also use sanitizers. Right, now, turns out that DCC actually uses some of these sanitizers behind the scenes. It was just hidden from you. But the ones that are highlighted are some of the ones that we use. Right, so sanitizers are tools that add extra error checking code into your program so that when a problem occurs, the program stops immediately. You get a nice error message detailing where the error occurred, where the error occurred, and the specific functions that were called, the line number, and so on. Okay. And yeah, we will be using address sanitizer, bleak sanitizer, memory sanitizer, and undefined behavior sanitizer. Yeah.
What's ASAN and UBSAN?
So ASAN and UBSAN, so these are short for address sanitizer and undefined behavior sanitizer. Yeah. All right, so now I'm going to just talk a bit about the different sanitizers. In the lab exercise, you'll go into a lot more detail about those. So I'm just going to briefly introduce them. So the address sanitizer detects invalid memory accesses. Right? So things like when you're trying to access null, when you try to access an index which is out of bounds for an array, if you're using a piece of memory after you've already freed it, if you're trying to free memory twice, and so on. Okay, and to use address sanitizer, we compile with this flag, right? So in addition to these flags here, we also include this flag, minus f sanitize equals address. All right, so here's an example of an error that would be caught by address sanitizer. All right, so this program over here creates an array of size 5, and it reads values into the array. Right, so we use scanf to read in numbers into the array. Right, now have a look at this program and tell me if you can see any problem with this. Yeah. Sorry?
If you scan in more than 5, it's going to go out of the array.
Yes, perfect. So if you scan in more than 5 numbers, if you type more than 5 numbers before pressing Control D or something, then it's going to try to insert the numbers after the end of the array, right? So that's going to be a problem, right? You're accessing memory that you shouldn't be accessing. So address sanitizer will determine that there is an error, and it'll give you a nice, long, and hopefully not scary error message like this, right? And this is the kind of error message that you'll get. And in this week's lab, and this is might look scary, but it actually contains a lot of useful information. So in the lab, you'll get some practice with picking things out from these error messages. Yeah.
Is this only in the terminal, or is it saved to like a text file?
This is in the terminal. Yeah. So the error message will appear in the terminal. Cool. So now for another sanitizer called leak sanitizer, right? So this sanitizer detects memory leaks, right, as the name suggests. And here is an example of an error that would be caught by a leak sanitizer. So we malloc an int, right, and then we don't free it at the end of the program, right? So very, very simple example of a leak. Obviously in your labs and assignments, it might be a bit more tricky to figure out where the leak is coming from. But the leak sanitizer will give you information about where the memory that you allocated was leaked. Right, so very useful. Right, we also are going to be using memory sanitizer. Right, so memory sanitizer detects uninitialized memory access. Right, so not invalid memory access, but accessing memory which is uninitialized. Right, so here's an example of an error that would be caught by memory sanitizer. We create an array of size 10, but we don't initialize it, right? So notice that we're not initializing any of the elements. We set one of the elements, so we've initialized one of the elements of the array, but then we try to check the value of another element, right, in an if statement, right? And this means we're accessing uninitialized memory, right? Because if we don't initialize an array, right, or a variable, then the value of that variable is unknown, right? It's going to be whatever was in memory at the time that the variable was created, right? So essentially junk value, right, garbage value. So this sanitizer will make sure you're not doing any of that, right? Because if you have, if you're accessing uninitialized memory, then your program might do different things each time it's run. Yeah.
If you have a thing where, say, for example, you're reading into an array, right?
Yeah.
An array of length 5, and
Yeah.
then you read into it, but you can choose to stop reading in early, right?
Yeah.
By Control D. So, for example, say the user only enters in 3 values,
Yep.
and then Control Ds, but then after that loop in your program, you're choosing to check the value of the 5th element, right?
Yeah.
Would this sanitizer be able to warn you of it potentially being uninitialized depending on how early a loop ends?
Yes. So the sanitizers run during runtime, during the runtime of the program. So it'll keep track while the program is running of what is initialized and what isn't. And if you try to use an uninitialized value in an if statement, then it'll complain.
So sanitizers change the code that is generated as well. It's not just
Yes.
used in like.
Yeah. So yeah, it adds extra code, extra machine code to the program to check things at runtime. Yeah. Okay. So there's also undefined behavior sanitizer called UBSAN, and this sanitizer detects a wide range of undefined behaviors. Right. So things like integer overflows, integer underflows, and so on. So here is a very simple example of an error. So you create a variable which is the largest possible int, then you try to add a value to it, right? And that would cause an integer overflow. So UBSAN will stop the program and yeah, tell you what happens. All right, so those are the sanitizers. Now, yeah.
Would there be any overlap between like what errors they pick up between the four sanitizers?
There can be a little bit of overlap. So I know that if you try to dereference null pointer, then address sanitizer will pick that up, but also a UBSAN will pick that up too. So yeah, sometimes the errors would double up, but yeah.
You mentioned the uninitialized memory access, but what if you malloc that and then you don't assign a value to that second element, but then you still use that? Technically, it's initialized because you malloc that memory.
So when you malloc a piece of memory, the memory in the memory block that gets returned is uninitialized. So if you try to use any of the values without initializing them, then you'll get an error. Yeah.
Is it free null? Doesn't it just do nothing?
Yeah, free null does nothing. Yeah.
So what did you say earlier about how they both might pick up on dereference?
So if you dereference null, yeah. Yeah, okay. Yeah, so another tool that we have is called valgrind, right? And valgrind is good for finding memory leaks and finding memory errors. So if you want to use valgrind, the problem is we can't use all of these tools at the same time, right? Valgrind isn't really compatible with address sanitizer, so in order to use it, you need to compile without ASAN, and the lab actually shows you how you can compile things without ASAN. All right, and the most important tool is called Make. Right now, I've already showed you the kind of compilation commands that we use in the course. Right, they're all going to be quite long. So in this course, we actually don't type these commands. What we use is a Makefile. Right, and a Makefile lets you specify all the executables that you're going to create and all their dependencies, right? So all the C files that they depend on. And when you type make, so if you have a Makefile and you type make, then it'll automatically determine what needs to be compiled and also generate the compilation command and run them for you. Okay, so in the course, you might never need to type a compilation command like this, right? Or maybe except for the first lab, but yeah. In most of the course, all you're going to need to do is to type make. Yeah.
Will make in the error message distinguish of the like original compilations that it finds like an error in? Like the compilation commands, like for example the memory sanitizer or
So the sanitizers will give you errors at runtime, not at compile time. So when the program compiles, it'll give you an error if there's a syntax error, but not when there's invalid memory access, because those are things that are detected at runtime. Did you have a question?
Yeah, so the dash W or the dash W error,
Yeah.
those are checking for syntax errors during compilation. And
Yes.
the sanitizers are adding machine code that will do sanity checks during runtime.
Yeah, perfect. Yeah. So So WAll and WError, those check for syntax errors at compile time, and the sanitizers detect errors at runtime. Okay, so with that, that's going to be all the tools, the extra tools that we use in the course. And if you're still not sure about Sanitize and Makefiles, the first week's lab is going to be all about those. So don't worry, there's much more detail in the lab exercise. So yeah, that is the end of the introduction. And so since we ended at just the right time, we'll take a 5-minute break and then we'll get back and talk about our first topic, which is recursion. All right, so yeah. Okay, so let's get back into it. Right, let's get started again. Okay, so the first topic that we're going to be talking about is recursion. Right, very, very spooky. So we're going to talk about recursion, go through basically a boatload of examples to hopefully get you to understand how recursion works. Okay, and also the slides are now up on the course website, so you can follow along if you want. All right, so yeah, here is recursion in a comic. So by the end of this lecture, you'll understand what this is all about. Okay, so first of all, what is recursion? Right now, you probably heard of the concept of recursion before, and the definition that you might have heard is when a function calls itself, right? And it is true that a recursive function is a function that calls itself, but I want you to think of recursion more broadly, more generally, as a problem-solving strategy, right? Where we solve problems via solving smaller or simpler versions of the same problem. Right, so think of recursion as this. Okay? Now, before we even go into any coding examples of recursion, we're going to start with this example over here, right? Building a pyramid, and this is from a game that you might have heard of before. But suppose that I'm playing the game, and I see one of these pyramids, and I think that looks pretty nice, and I want to build one myself, right? So I ask you, how can I build this pyramid? Right. So one way that you might explain how to build a pyramid, is this specific pyramid, which has width 7, right? 7 blocks across, is to build them in layers, right? So first of all, I need to build one layer of, one 7 by 7 layer of blocks, right, as the base. And then on top of that, I want to build a 5 by 5 layer of blocks. And then on top of that, a 3 by 3 layer. And then on top of that, a 1 by 1 layer, which is just a single block, right? So this is what I would call an iterative method, right? Because we're iterating over the widths, and we're building a layer each time. Right, so this is how we would kind of describe it in words. Right, so to build a pyramid of width n, so let's assume that n is odd here, so that the top of the pyramid is just a single block. So for each width, w from n down to 1, right, decrementing by 2 each time, we're going to build a w by w layer of blocks, right? So a square of width w, layer of blocks on top, right? And that's an iterative method, right? Now, what I'm going to, that's how you could describe how to build the pyramid. Now, another way you could describe it to me is to build a 7 by 7 layer of blocks, right? And then the second step would be to build a pyramid of width 5, right? And if we do that, then you've got the whole pyramid, right? And that's what I would call a recursive method of doing things, because in this second step here, build a pyramid of width 5, we're essentially doing the same thing, right? Building a pyramid, except the pyramid is smaller, right? So this is what I would call a recursive method, right? And if we were to write this up, describe this in English, we're not going to code this up. Here's how we might describe it, right? So to build a pyramid with n, we first of all build an n by n layer, right? And then we build a pyramid of width n minus 2, right? So example, let's suppose we want to build a bigger pyramid of width 11, right? So what we do is we build an 11 by 11 layer of blocks, then we build a pyramid of width 9, right? Then I ask you, well, how do I build a pyramid of width 9? Then you say, well, we build a 9 by 9 layer of blocks, then we build a pyramid of width 7, right? Then I ask you, how do we build a pyramid of width 7? Then, it just goes on until we've built the entire pyramid, right? Now, there is actually a slight problem with this description. If we were to try and get a computer to understand this, right? So if we somehow took these instructions exactly and converted them to code, there would be a problem with the program. So can someone identify what that problem is? Yeah.
When it reaches a width of 1, it will try and build a pyramid of width -1 like that.
Yeah,
Yes.
perfect. So
That sounds sort of problematic.
yeah, so if we try to build a pyramid of width 1, right, then by following the instructions exactly, because that's what a computer does, right? It just does what we tell it to do. We build a 1 by 1 layer of blocks, and then we try to build a pyramid of width -1, right? So a computer isn't going to quite understand what we mean there. As humans, by following these instructions, when we eventually get to n equals 1, right, we would just stop, right, because we know that a pyramid of width -1 doesn't quite make sense, right? But computer would kind of get confused about that. So what we need is a stopping condition, right? Something to tell the program that we no longer need to recurse, right, and we can just stop. And that's what is called a base case, right? Yeah. So here is a better version of the solution. So to build a pyramid of width n, if n is 0 or less, right, so including if it's -1, then we do nothing. Otherwise, we build an n by n layer of blocks, right, and this is basically what we had before. So we build an n by n layer of blocks, then we build a pyramid of width n-2 on top. Right, so that's just one example of recursion, right? And now we'll start getting into some actual code examples. Right, so here's a classic example of recursion. Right, so calculating the factorial. Right, now I'm guessing most of you know what factorial is, but in case you don't, the factorial of a number n is the product of all the numbers or all the integers, or the positive integers less than or equal to n. Right, so n factorial is equal to n times n-1 times n-2 times blah 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 all the way down to 1. Okay, so that's factorial. And if I asked you to implement a function that calculates factorial with your 151 knowledge, you might implement it as a while loop or a for loop, right? So we start off with a variable that is 1, and then we do a for loop and multiply each integer by I, right? And at the end, we get n factorial and we return it. Yeah.
How do we decide which one is better to use? Like whether we should do it recursively or iteratively?
That is a good question, and it is a question we'll get to at the end of the lecture, actually. So it's a long way until we talk about that, but yeah, good question. All right, so yeah, so that is an iterative method of calculating factorial, right? Now, factorial can be also implemented recursively, right? And in order to think about how you do it recursively, you need to make an observation, right? Now, with all recursive solutions, you need to think about it a little bit and make an observation, right? So the observation here is that n factorial is this, huge formula, n times n-1 times n-2 times blah, 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 all the way down to 1. But that, right, but we notice that n-1 times n-2 times blah, 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 all the way down to 1, well, that's just n-1 factorial, right? So n factorial is actually equal to n times n-1 factorial, Right, so here's where the recursion comes in, right? We're solving a problem via solving a smaller version of the same problem, right? So our original problem is n factorial. The simpler or smaller problem is n minus 1 factorial. And we call the smaller version of the problem a subproblem, okay? So you might hear that term in the lecture. So for example, 4 factorial is just equal to 4 times 3 factorial. Right? And 3 factorial is 3 times 2 factorial, right? And so on. Right now, if we use this observation to implement our program, implement our function recursively, then this is what we might do, right? Int factorial takes in an integer n and returns n times factorial n minus 1. Right now, of course, can you guys see the flaw in this program? Yes, so a lot of hands, right? Yeah, you wanna?
There's no stopping condition. You just
yes.
it'll go negative.
Yes, exactly, right? There's no stopping condition again, right? So what we'll end up doing is we'll end up trying to find factorial of -1, factorial of -2, and so on, right? Which is a problem. So again, that's the problem with the function. There is no stopping condition, no base case. Right, so the correct way of doing it is you would add a base case, right? So check if n equals 0. If n equals 0, then we return 1, because 0 factorial is 1. Otherwise, we do what we did before, right? We multiply n by factorial of n minus 1. Okay. Cool, so that's factorial. Now, based on these examples, you might think that factorial, well, that's just another method of, that's just another way of implementing a loop, right? Because what we've done so far is I've showed you the iterative method, which is just a loop, and it turns out that we can just use recursion instead, right? So even though that is sometimes true, recursion is much more broader than that, right? It is, solving a problem in terms of solving smaller versions of the same problem, right? So here is an example which might not be so, and this is how we would evaluate factorial, right? So you can have a look at this. Now, here's an example which might not be so easily implemented iteratively. Right, so Fibonacci sequence. Right, so I'm assuming most of you know what the Fibonacci sequence is, but just in case you don't, this is how it's defined. Right, so the Fibonacci sequence is a sequence of numbers where each number is the sum of the 2 previous numbers. Right, and the sequence starts off with 0 and 1. Right, so we start off with 0 and 1, then the next number is going to be 1. But then the next number is going to be 2, the next number is going to be 3, and then 5, and then 8, and so on. Right, and this is how we would express it, right? So f of 0 is 0, f of 1 is 1, and f of n is f of n minus 1 plus f of n minus 2. Right, now, if we try to implement this iteratively, we might encounter some challenges, right? Because each Fibonacci each Fibonacci number is expressed as a sum of 2 smaller Fibonacci numbers, right? So it keeps branching off, and so you're going to have to calculate all of these terms, right? And if you're using a loop, how can you keep track of what you've calculated and what you haven't calculated yet, right? So it might not be so easy to convert to a loop, right? So here is how we would implement Fibonacci recursively. Right, so if n equals 0, we return 0. If n equals 1, we return 1. Right, so we're trying to find the nth Fibonacci number here. And otherwise, we return the n minus 1th Fibonacci number by calling fib n minus 1 plus the n minus 2 Fibonacci number, which is fib n minus 2. Okay, so here is actually an example of where there are multiple base cases, right? In general, you can have more than one base case. And you can also have more than one recursive case. Right, so there'll be some examples of that in the tute next week. Okay, so these are some examples of recursion. Now let's talk about a bit more about how recursion actually works. Right, so a recursive function is a function that calls itself. Right, so wouldn't that be problematic for the program? So turns out no, right? And so recursion is perfectly fine, and the reason is that there is a difference between a function and a function call, right? So a function is just a set of instructions, right, that the computer follows. Think of a function as like a recipe, right, for something. So you just got one recipe, and a function call is a specific instance of the function, right? So you're following the recipe, and what you end up with is a something like a cake or something. Right. So the function code lives in one region of the memory of a program, right? And there's only one copy of that. But every time a function is called, the program creates a stack frame in memory for the function call. Right? So each function call I've written here creates a new kind of mini environmental box called stack frame, right? And the stack frame holds all the local variables used by the function call, right? And to demonstrate that, here are some examples of programs. Right, so here's a program where there is no recursion, just to introduce the idea of a stack frame. Right, so the main program is the first program that's going to be called. Right, so when the program starts, there's going to be a stack frame for main on the stack. Right, now the main function calls A. Right, so once A is called, there's going to be a stack frame for A created right, on top of the main function. And now program A, function A calls B. Right, so once B is called, a stack frame for B is going to be created on the stack on top of A. And B just prints out some value. And once B returns, the stack frame for B goes away. Right, so now we're back in the A function. And once A returns, the stack frame for A goes away, and we end up with just the main function again. Right? And once main returns, the stack frame for main will also be gone. Okay, so that's how the memory of our program changes while it's running. Okay, now here is how a recursive function would work, right, in terms of stack memory. Right, so let's consider a simple example of calculating Fibonacci factorial 2. Right, so finding 2 factorial. So what happens, right? Well, when the factorial function is initially called, right, a stack frame for that is created, right, where n is equal to 2. Right, now factorial 2 is equal to 2 times 1 factorial, right? So it's going to have to figure out what factorial or what 1 factorial is first, right? So it's going to call factorial on 1, and that's going to create another stack frame for factorial 1 on the stack. Right? Now factorial 1 is going to call factorial 0, so that's going to create a stack frame for 0, factorial 0 on the stack, and once factorial 0 returns 1, the stack frame for factorial 0 goes away. So after that, we can now calculate factorial 1, right? Because factorial 1 is 1 times 0 factorial, which is 1. So factorial 1 now returns 1. So the stack frame for factorial 1 goes away. And now factorial 2 can finally calculate what 2 factorial is, which is 2. Right? So factorial 2 returns 2, and the stack frame for factorial 2 goes away. Okay, so that is how recursion works, right, in terms of the memory. Okay, now if we have an even larger number that we want to calculate the value of, we want to calculate the factorial of, then we're going to have even more stack frames, right? So if we try to calculate factorial 4, we're going to end up with 5 stack frames on the stack at a particular point, right? And then eventually all of these stack frames are going to disappear. Right, yes?
Is it always symmetrical?
So the question is it always symmetrical? And the answer is it depends on the function. So for a simple function like this, where you've got just one recursive case and one base case, then it'll probably be symmetrical. But there are some cases where the stack can grow and shrink. Yeah, so not always symmetrical. It depends on the function.
Would we be seeing a lot of those questions like in this
Sorry?
Would we be seeing a lot of those types of questions like for recursion?
So the question is, are we going to see lots of examples of these questions? Yes, so we'll be going through a lot of recursion in the course. So yeah, don't worry if you're not quite clear on this after the lecture, because we'll go through lots of examples throughout the course. Yeah, and some terminology here is that when the stack is growing, we call that winding, right? So the stack is winding up. And when the stack is shrinking, we call that unwinding, okay? And now to actually show you that the stack is actually, a new stack frame is actually being created for each function call, I'm going to go over here to the factorial program. Right now, I already have the factorial function implemented here. But what I'm going to do is print out the address of the variable n, right? And I'm going to show you that the address changes every time the function is called, right? So here I'm going to add a print statement that says factorial of n, address of n is this. Okay, so this print statement is going to run every time the function is called, and we're going to see where the address of the variable n lies. Right? So let's compile and then run factorial, and the program takes in a number that we want to find the factorial of. So let's go factorial 5. Right, and we see that 5 factorial is 120, but also for each function call, we notice that the address of n is different, right? So in particular, it is decreasing, right, for every function call, right? So for every new stack frame that's created, right, each stack frame holds its own copy of the variable n, right? And in particular, when the stack grows, the stack actually grows towards lower memory addresses, right? So, yeah. Yeah.
So the stack going down is just because of how the stack and heap is located in memory, right?
Yes. So yeah, the stack starts off at high memory addresses. The heap starts off at low memory addresses, and they kind of grow towards each other. Yeah. Okay, and one more thing to take it even further. So I'm borrowing some terminology from later in the course, which is pre-order and post-order. But I'm going to use them here because it's kind of a neat way to describe them. But due to how the recursion works, right, if you put any operations before a recursive call, right, then they're going to occur during the winding phase, right, while the stack is growing, right? Now, if you put operations after the recursive call, then these operations are going to occur during unwinding, right? So while the stack is shrinking, right? So to demonstrate this, I'm going to go over to the factorial program again. Right, and I'm going to add some print statements, yeah?
Having two distinct stages of winding and unwinding,
Yeah.
that I'm assuming that only works if you have only one recursive call, right? Whereas if you were doing something like the Fibonacci sequence, wouldn't you be doing like two recursive calls per function?
So-
per function calls.
Right, yes. So the question was for the winding and unwinding phases, does that only occur when you have one recursive call, one recursive case? So for examples like Fibonacci, where you have multiple recursive calls, the stack does grow and shrink over the course of the function. So, yeah. And to show that for yourself, you can try and add print statements to your program. So what I'm going to do now is add one print statement to demonstrate the pre-order and post-order operations. I'm going to add one print statement before the recursive call. Right, so I'll just add it at the start of the program. So factorial of n entered. And I'm going to print out n. And I'm also going to change the structure of this function slightly so that we can actually print something at the end. So I'm going to say int result, and if n is 0, I'm going to set result to equal to 1. Otherwise, I'm going to set result equal to n times factorial n minus 1. And then I'm going to return res at the end. Right, and before the function returns, I'm going to print out that factorial is returning results. Okay, so I'm adding a print statement before the recursive call. I'm also adding print statements after the recursive call. And we're going to show that these print statements occur in opposite orders. Right? The one before the recursive call is going to happen in the same order as the function calls, whereas the print statement after is going to happen in reverse order. Right? So we're going to see that. Okay, so let's go with factorial 4. All right, so we see that initially factorial 4 entered gets printed, then factorial 3, then 2, then 1, then 0. And the print statements after the recursive call happen in reverse, right, as the stack is unwinding. Right? So factorial 0 prints out what it's returning first, then 1, then 2, then 3, then 4. Right? And if you think about it, that should make sense, right? Because when you put some operation before the recursion, right, then it's going to have to be printed first, right? So, before you even call the function recursively, you need to print out this statement over here. Meanwhile, if you put a print statement after a recursive call, then you can't print it until all the recursive calls print their print statements as well, right? So what's going to end up happening is the function at the deepest level of the recursion prints out its print statement first, then the ones that happens, then the functions that were called before it, right? Okay. Yes, so that's just some detail. Now, we've seen some examples of recursion on integers, right, with factorial and Fibonacci, right? And the way we solve those problems recursively is we call the function on a smaller number, right? For n factorial, we call the function on n minus 1, right? And for Fibonacci, we call the function on n minus 1 and n minus 2. Right? So now we want to look at linked lists, right? Because we can also solve problems on linked lists recursively. So how do we apply recursion to linked lists? Right. So the idea here is that if list is a pointer to a linked list, right, the first node of the linked list. Then a list next, which is this pointer over here, right, list next points to a smaller linked list, right? So the original list contains 3 nodes. Now list next is a pointer to a linked list that contains 2 nodes. Right, so in general, when we're solving linked list problems recursively, we call the function recursively on list next, right, to solve the problem on that smaller list, right, and that will help us solve the problem on the full list. Okay, so here is an example where we want to sum all the values of a list. Okay, so we have a base case. Our base case, we want to always handle the base case first, is if we have an empty list, right? So if the list is empty, then the sum of all the values is going to be 0, right? Because there are no values. So that's our base case. And what is our recursive case? So what happens if the list is not empty? Then what we'll do is, here's the kind of reasoning that we take. Right, so I can't solve the problem directly, so I don't know what the sum of the list is, but I do know that if I can figure out what the sum of the rest of the list is, right, and then I add on the value at the current node, that will give me the entire list, the sum of the entire list, right? So that's how we can approach this problem. Right, so here is an example of how we would evaluate the sum of a list recursively. Right, so sum of this list over here, well, I don't know what the sum of the list is, but I know that it's equal to 3 plus the sum of the rest of the list, which is just 1, 4. Right, now what is the sum of this list? Well, I don't know what that is, but I know that it's equal to 1, the first element, plus the sum of the rest of that list, which is just 4. Right, now what is the sum of this list? Well, I don't know what that is, but I know that it's equal to 4 plus the sum of the rest of the list, which is an empty list. Right, and now I know what the sum of an empty list is. Right, that's 0. So we can add. So now we can finally calculate the sum of this list, which is 4 plus 0, which is 4. After that, we can now calculate what the sum of this list is, which is 1 plus 4, which is 5. And then finally, we can figure out what the sum of the entire list is, which is 3 plus 5, which is 8. All right, so here is how we would implement summing a list. Right, so here is our node struct for a linked list. Right, each node contains a value and a pointer to the next node. And then here's our list sum function. Right, so our base case is where the list is empty, and in this case we return 0. Right. And otherwise, we take the sum of the rest of the list, right, list sum of list next, and we add on the value at the current node, which is list value. Okay, so that is how we sum a list recursively. Right, so any questions about that? Yes?
So I don't know if this is accurate, but I've heard that all recursive algorithms can be written iteratively, right? So
Yeah.
is there any practical reason, apart from readability, where you would actually want to do something recursively as opposed to iteratively?
Yes, so the question was, is there any reason why you would want to implement something recursively as opposed to iteratively? Yes. So even though almost all the examples in this lecture can be implemented iteratively rather easily, there are problems later on in the course where it is much easier to implement something recursively rather than iteratively. So yes, so there is a practical advantage of using recursion sometimes for certain problems.
Right.
That we'll cover later. Okay, so that is summing a list. Right, now let's talk about a more hairier problem where we actually modify the list. Right, so append the value to a list. Right, now, let's look at the function prototype. Right, the function takes in a pointer to a node called list, and it takes in a value. Right, and it inserts, so it should insert the given value at the end of the list and return a pointer to the start of the updated list. Right, now, first thing we should consider is why does the function return a pointer to the start of the updated list? So why does it need to do that? Any ideas? Yeah.
If it's appending to an empty list, you have to return the pointer to that first element.
Yeah, great. So if the list is empty, right? So if the list is empty, then after we append a value to it, right, the list is now going to contain one node, and that node is going to be the head of our list, right? So we need to make sure to return the new head of the list just in case it changes, right? Now, in this example, the only time the head of the list changes is when the list is empty, right? In all other cases, the head of the list remains the same, right? But this is why we return the head of the list in this function. All right, so let's try and implement list append, right? Now let's try and think about this recursively. So our base case, right, as I suggested, is if the list is empty. Right? So I'm gonna open list append here, and I'm gonna write some code to handle this base case. Right, so what this program does is it repeatedly reads in values and calls list append. Right, so it's gonna every value that it reads in, it's gonna append a value to the list, which starts off as empty. Right, so let's try and implement this. If list equals null, right, if the list is empty, then we create a new node and return it, right? So I already have a function for creating a new node, so I'm just going to call it. Right, so call a new node and then return. Right, otherwise, right, so here's the reasoning. Right, so if the list isn't empty, then let me just append the value to the rest of the list, right? Which could be empty, could not, which might be empty, might not be empty. Right, so we're going to call list append list next and value. Right, and what do we return at the end? Well, let's think, right, because the function should append the value to the list and return the head of the updated list, right? If the list isn't empty, then the head of the list doesn't change, right? It's still going to be the head of the list after the value is appended. So what we do is just return list, right? And that is our attempt. Now I'm saying attempt because there's a possibility that it might not work. So let's compile and run program. And I'm going to enter some values here, 1, 2, 3, and let's see what we get. Right, so we only get one value in our list. Right, one, so we are expecting 3 values, but we only got 1. Right, so what is the problem with our program? Right, so here is what I just implemented. Right, and what is the problem with our code? Any ideas? It's very subtle, the problem, yeah.
We're not linking the node that we want the new node to the end. It's just like sitting there by itself.
Yes, perfect. So the problem is we're not linking the node that we created to the end of our list, right? So here is an example of why this doesn't work. Right, so consider this list, all right? So it's called myList, and I'm calling the function to append 5 to the list, right? Now, let's run through the function and think about what's going to happen, right? So the list isn't empty, Right, so here's my original list. The list is not empty, so we're going to call list append on list next, right? Now, what is list next? List next is null, right? So this function call is going to return a new node, right? It's going to return a new node containing the value that we're trying to insert, which is 5. The problem is that, well, we're not doing anything with the node after it gets returned from this function, right? So the node is just sitting there and it's not getting linked to the list, right? And if you look at the code, it should kind of make sense, right? Because the only way you can link the node to the original list is if you set the next pointer of one of the nodes, right? If you say list arrow next equals something, right? But there is none of that in this code, right? We're not setting the next field of any nodes. We are passing list arrow next to, the list append function, but we're not setting it to anything, right? So the new node doesn't get attached to the list is the problem. Yeah.
Can we do something like struct node something equals list append, and then you say struct node next is whatever?
Yeah, so that's one way of doing it. So here is the solution for, here's the right solution for this, right? And there's only one change from our previous attempt, right? Which is that after we call list append on list next, we need to set list arrow next to this function call, right? So whatever this function returns. Right, now, this is a common pattern that you'll use whenever you need to modify a list, whenever you need to insert something into a list or delete something from a list, right? So, and this might be confusing, right? Because there's a lot going on in this line. So let's try and explain what's going on here. Why does this work, right? So how you should think about it is you should try to read it from right to left, right? Because the function is being called first, and then this part happens afterwards, right? So consider this list, right? So we have one node, and after this node, there is the rest of the list, right? So this list contains at least one value, and we have two cases to consider, right? Either the rest of the list is empty, or the rest of the list is not empty, right? Two cases, right? So case 1 is that the rest of the list is empty, right? So what happens if the list is empty? Well, we know from what the function does, from the function definition, that this function call over here, right, list append list next, right, list next is null because the rest of the list is empty. This function is going to return a new node, right? So list append list next value will return a new node, and then here is the left part, right? List arrow next equals, right? That is going to cause the new node to be attached to the list, right? So this is the change that happens as a result of list next equals list append, right? So this assignment over here sets list next to point to the new node, okay? So that's the case where the list is empty, and this kind of pattern ensures that the new node gets attached to the list. All right, now here is the second case, right? The rest of the list is not empty, right? Now, if the rest of the list is not empty, right, then this means that there's going to be at least one node, right, in this part of the list. So I've just drawn it as a circle, and the value doesn't matter. Right, so here's what the rest of the list looks like. Now, what is list append going to do? What is this function call going to do? Well, assuming that the function does what it's supposed to do, right, it's going to append the value to the rest of the list, right? So it's going to add the value to the end, and it's going to return a pointer to the start of the rest of the list, right? And since this rest of the list here, this wasn't empty, the function is just going to return back the pointer to the first node of this part of the list, right? Now, yeah, so I've color-coded these blues so you can see what, so this is what the function here is returning. It's returning a pointer to this node over here. Right. Now, what does this list arrow next equals part do? Right, so this causes list next to point to whatever this function call returned, right? Now this function call returned a pointer to this node over here. So this assignment is going to end up causing this node here to point to this node, which it was already pointing to, right? So you see, if the list is, if the rest of the list is not empty, then this line over here, this part of the line, list arrow next equals, sort of doesn't really do anything, right? But if the rest of the list is empty, it does do a lot, right? It attaches the new node to the rest of the list, right? So that's a sort of more detailed explanation of why this works. Okay, so do we have any questions about that? Yeah?
In line 3 or slide?
Line 3, yep, let me go back.
Yeah, it says if list equals to null, then return you null
Yep.
value. Wouldn't that stop the recursion process because you just return that new node to the
So this is a stopping condition, so this is a base case, but it doesn't, it returns the new node to whoever called it, right? Whoever called this function. So the caller of this function might be the main function, it might be another instance of the list append function, right? So if we have a list with one node, then list append is going to be called on this node, but then it's going to call list append again on an empty list, right? Because the rest of the list is empty. And that function call is going to return a new node back to the original list append function call. And then the new node is going to get attached to the list. Yeah, so when the function, so when we return from a function, you know, it doesn't just return to main, it returns to whoever called the function. Yeah. So hopefully that makes sense, but if you want, I can drop a diagram. If you go to a help session or consultation, we can help you explain that. Okay, so those are some examples of writing, using recursion with linked lists. Right, so now, so I've shown you a bunch of examples. Now, how do we actually write a recursive function? Right, because I've gone through examples, but you might, so going through examples is nice, but it doesn't really teach you how to do it yourself, right? So here are some of the steps which you should follow when trying to write a function recursively. Right, so the first one is to make sure that recursion is actually appropriate for the problem that you're solving, right? Because what is recursion? Right, recursion is solving a problem via solving a smaller version of the same problem, right? Now, if solving the smaller version of the problem is not going to help you solve the original problem, then recursion is not going to work, right? So you wouldn't use recursion. But yeah, first check whether recursion is appropriate. Then identify the base cases. Right? So the base cases are the problems that are so simple that no recursion is required. Right? So example of that would be 0 factorial, right? 0 factorial is 1. Right? Then identify the subproblems. Right? So the example for factorial is we need to find factorial of n minus 1. Right? So that's the subproblem. Now, when we're writing our solution, we need to assume that the function already works for the subproblem. Right? So that's the tricky thing with recursion. you identify the subproblem, you need to assume that the function already works, right? And if this sounds, absurd, like why are you assuming that it works already? Think about mathematical induction, right? And you might be familiar with this from high school or from math, right? When you solve things when you try to prove something with mathematical induction, you first prove a base case, right? Then you assume that the statement is true for some arbitrary value of n, right? For n equals k. And that's the inductive hypothesis, right? And then you try to solve, then you try to prove that the statement is true for n equals k plus 1, right? So that is kind of like what we're doing here, right? So we assume that the function works for the subproblem, then we try to use that result to solve the overall problem, right? So for the factorial example, we call factorial on n minus 1, and assuming that factorial of n minus 1 works, if we multiply it by n, that gives us n factorial, right? So yeah, this is really important. Assume that the function works. And then you got to think about how to relate the original problem to the subproblems, right? Knowing the result of the subproblems, how do you use that to solve the overall problem? Okay, so those are my steps for how to write a function recursively. All right, now I have a couple of exercises. So these are all on linked lists. So let's try and solve the first one, and then we'll continue on in the next lecture. Right. So what's the first exercise? So given a linked list, we want to print the items in the list in reverse. Right. Now this is a problem where what I just talked about, assuming that the function already works, is really important. Right. Now let's try and do this. Vince, I'm going to open this file. All right, list print reverse. Right. Now, how do we start off? Well, we want to try and implement our base case first. Right. So, what is our base case for this function? Yeah.
Empty list.
Yeah, perfect. So the base case is an empty list, right? So if list is null, then if the list is empty, then we don't really want to print anything, right? So I will just return. Right, if the list is not empty, what should we do? Because we want to print the list in reverse, right? Yes.
We list print reverse for the next node, and then we print the value of the current.
Yeah, perfect. So what we want to do is print the rest of the list in reverse, right? And then print the current value, right? Because we don't want to print the current value first, because that would be printing, in forward order, right? In order. But what we want to do is print in reverse, print the rest of the list in reverse, right? And then print the current value. So list print reverse, list next. Now here's where assuming that the function works correctly is important, right? Because while I'm implementing this, right, I don't know what list print reverse is doing, right? Because I haven't finished implementing the function yet. But assuming that the function works, right, it should print the rest of the list in reverse, right? So, assume that my list contains the values, 1, 2, 3, 4, and 1 is my first node, right? Then list print reverse, assuming that it works correctly, should print 4, 3, 2, right? Right, so that's my sort of inductive hypothesis, right? And after it has printed 4, 3, 2, now I can print out 1, right? Print out the current value. So let's compile this program and run it. And I'm going to enter some values here. Let's go with 1, 2, 3, 4, 5. right? So the original list is 1, 2, 3, 4, 5, but the reversed list is 5, 4, 3, 2, 1, right? So our function seems to work. Right now, let's try a couple of base cases. So edge cases. So an empty list gets printed out, as it should. Just nothing gets printed out. What happens when you have only one value? Well, it just prints out that value, and so our function seems to work correctly. All right, now we have run out of time, so we will continue on in the next lecture. All right.